We finally made it to the section where we discuss the derivative rules. We've been finding the derivative at a particular point or the derivative function by taking the limit of the difference quotient. Now, this is always an option, but it is time consuming, and there are times when it's algebraically quite difficult. We now turn our attention to the derivative rules, which will allow us to find the derivative either at a point or the derivative function without having to resort to taking the limit of the difference quotient. This will make your life much sweeter. Now, this is a super important section that you need to master at the 95% level or above. Taking the derivative becomes a small part of what you do in Calculus 2 and 3. You have to be very accurate at finding derivatives. Let me share my screen with you and we'll get started. We start with the learning derivatives. We're going to find rules for the derivative of a constant multiple, and power rules. And then we're going to learn rules that apply to sums and derivatives of functions. We'll then learn what's called the product rule, or the product of two functions where we want to find the derivative. Then we'll learn the quotient rule when we want to take the derivative of the quotient of two functions. The product rule and quotient rule will not be as simple as it was with limits. The derivative of a product is not the product of derivatives. Then we'll extend the power rule for negative exponents. And in fact, I'll let you know that it will work for all real values. Then we'll combine these different differentiation rules together and look at several examples. The two building blocks for polynomials are constants and power functions. Just c and x to the n, where n is a counting number. So we'll start with the derivatives of those. The derivative of a constant is going to be 0. The constant corresponds to a horizontal line, and the slope on a horizontal line is constantly 0. So we know now that the derivative of a constant, like 5, has to be 0 because it's a horizontal line. Now, we can represent this down below by writing the derivative of the constant equal to 0. That means that if f of x equals c, f prime of x equals 0. It also means, using Leibniz's notation, that the derivative with respect to x of a constant equals 0. Now, this applies to all constants. So if I try to trick you on an exam, and I write something like the derivative with respect to x of pi squared, you better tell me that that comes out to be 0. Pi squared is a constant. Derivative of a constant is 0. Let's see why this is so by looking at the definition of the derivative, the limit of the difference quotient. Since the function is a horizontal line whose value is constantly c, f of x plus h is c, and f of x is c. In the difference quotient, this gives us 0 divided by h. Remember, in the limit, we never quite get to h. So h is not 0. It's approaching 0, but it's not 0. 0 divided by a non-zero number is 0. It's okay to have 0 in the numerator, just not the denominator. And this tells us the limit as h approaches 0 of 0, well, the limit of the constant 0 is 0. Let's now look at an example. I don't need this much space because I can tell you right away that the derivative with respect to x of g of x has to be 0 because the derivative with respect to x of -3 is 0. The derivative of all constants is 0. If I were to write the derivative with respect to x of Euler's number e, me 0. If I were to write the derivative with respect to x of the square root of 11, give me 0. Let's now take a look at the power rule. When we look at the power rule, we're looking at power functions. The variable x raised to some counting number power, like 1, 2, 3, 4, 5, and so on. We will extend this rule to negative powers, x to the negative n, but these are no longer called power terms because the variable won't show up in the numerator with a positive exponent. Then finally, we'll be able to extend it to rational functions or rational values and to real exponents. I'll let you use the full power from this section on. Basically, the power rule works for all x to the n where n is a real number. Let's take a look at the power rule now. Suppose n is a counting number. If the function is equal to x to the n, for example, let's suppose that we have a function up here, f of x equals x to the 5th power. It's not a derivative, that's a power. Then the derivative of the function is found by pulling the power to the front and multiplying by it as a constant and reducing the power on the variable x. This means that f prime of x is equal to 5x to the 4. This is why taking the derivative of a polynomial reduces the degree by 1. So the derivative of all quadratics, degree 2, must be lines, degree 1. Let's go ahead and prove this rule now. We're going to use the binomial theorem, which basically gives us the coefficients when we take a binomial to a power. For example, if we were to take x minus a and raise it to some nth power, I would get a lot of terms with x to the n, and then plus or minus constants times x to the n minus 1 times a to the 1st, plus or minus more constants, x to the n minus 2, a squared, and so on, all the way down to x times a to the n minus 1, plus or minus some constant times a to the n. In other words, when you expand a binomial through multiplication, it goes down on one of the variables and up on the other. So 5, 4, 3, 2, 1, not there, and not there, 1, 2, 3, 4, 5. In our case, when we're looking at it, we can use this notation here called n choose k, which allows us to compute these question mark coefficients that go inside of the expanded binomial. Factorial means to multiply by that integer value and all preceding positive integers down through 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Let me write that up here for those of you who are not familiar with factorials. We will see factorials again quite frequently when we get into calculus 2. They get used quite often when we're looking at series. Now let's take a look and just know, don't have to memorize this, just know that these representations here give us the coefficients in the multiplied out binomial. Now let's apply this to our x to the n. We want to find the derivative by taking the limit of the difference quotient. This means we substitute x plus h for x inside of x to the n. It represents this representation on the right. Now we're going to use the binomial theorem to expand the first term in the numerator, just the x plus h to the nth power. Notice it comes down in the n values on the powers of x and up in the powers of h. The coefficients are given by this n choose k, starting with n choose 0, which is always 1. And then you have n choose 1, n choose 2, n choose 3, all the way out to n choose n. When we look at these, if we subtract the x to the n, this second term here, and we move it to the other side of the equation through subtraction, then we can rewrite this expression in this equation form. That just moves this one term to the left. And you can see what I'm trying to do. I'm trying to build the difference quotient. Now I take that simple expression and I divide both sides of it by h. Again, I'm trying to find the difference quotient to find a formula for the derivative. Now on the right, every term over here has an h in it. When I have h in every single term, then it becomes a common factor, which I can factor out. When I factor it out and simplify it with the h in the denominator, I get the expression that you see here. Notice that the first term no longer has an h because those cancel completely. But every term past the first term does still have h in it. The next thing we do, of course, is take the limit of the difference quotient as h goes to 0. This causes all the terms in this expression to go to 0, except the first one, nx to the n minus 1 power. And that is what we were trying to prove. We've reached the end of the proof, so we write QED. So, by that means, how can we find the derivative of x to the 7th? Or x to the 3rd in example 3. There's no point in pausing. It just doesn't take that long. F prime of x is equal to 7x to the 6th. Remember, we are pulling the power to the front and multiplying by the power as a constant and reducing the power on the variable by 1. Could I keep going? Of course. If you wanted to find higher order derivatives, you could continue taking the derivative. The second derivative in example 2 would be 6 times 7 x to the 5th, or 42x to the 5th. And I could keep going. You can imagine that as we decrease, at some point, that power is going to be 0. This always happens for polynomials, not other types of functions, but for polynomials it does. We say the derivatives eventually 0 out, and then they become 0 from there on. Because we have a constant at the front, the derivative of a constant eventually becomes 0. Now let's look at the sum, difference, and constant multiple rules for differentiation. So far, we've only dealt with single-term polynomials, a constant by itself or x to the n. But most of our functions have combinations of these. So we want to have combinations as well. For the sum rule, we have two functions, f and g, and they're both differentiable, meaning the derivative exists where they're defined. The derivative of the sum of the function f and the function g is the same as the sum of the derivative of f plus the derivative of g. In other words, the derivative of f of x plus g of x, a sum, is the sum of the derivatives, f prime plus g prime. Let's go ahead and prove this rule now. We want to start with the statement of the definition of the derivative by letting j of x represent this function f of x plus g of x. We don't use h for the name here because h is used in the denominator to represent the change in x. The next thing that we want to do after writing it in terms of this function j is replace that with what j represents, the sum of the two functions. So I can replace this j of x plus h with f of x plus h plus g of x plus h. And I can replace j of x with f of x minus g of x. Then I rearrange and regroup the terms. I switch the order of the middle two and write f of x plus h minus f of x plus g of x plus h minus g of x. Yes, you can see it. That's the difference quotient. We know that we can apply the limit laws. And the limit of a sum is the sum of the limits, which allows us to separate it out. Now we have the limit of the difference quotient with f plus the limit of the difference quotient with g, which tells us that the derivative of a sum is the sum of the derivatives. We have a very similar rule when we get to the difference rule for differentiation. The only difference, unintended, is that the function is defined to be f of x minus g of x. So again, to prove that this becomes the derivative of f minus the derivative of g, we let j of x be the difference this time, f of x minus g of x. And we write the definition of the derivative using j, and then we substitute in the value of j, which is f of x minus g of x. That means that we are replacing this part here with these two parts, and we're replacing this part with these two parts. Then we do a similar thing by rearranging terms. In this case, we want the f of x to come over next to the f of x plus h, and g of x plus h to join the g of x. We have to be a little careful with the signs, and in fact, we factor out a common negative from the ones with g. This then gives us the difference of the difference quotients. Limit of a difference is the difference of the limits. That allows us to split it into two limits. This is the definition of the derivative of f, and this is the definition of the derivative of g. So we've proved the difference rule. Let's now take a look at the constant multiple rule for differentiation. I've already used it once today when I took the second derivative of x to the 7th. It says if you have differentiable functions and k is just some constant number, pi, 5, cube root of a negative 42, and the derivative then of the constant k multiplied by the function is the same as if I factor the constant out and then take the derivative and remultiply the constant. The derivative of k times f of x equals k times the derivative of f of x. Let me write down an example for this one. When I'm looking at this one, I could write something like f of x equals 7x to the 5th. The derivative of f with respect to x means take the derivative with respect to x of 7x to the 5th, but I can factor the 7 out, not the x to the 5th, because that variable depends on the differential dx in the denominator. And I can take the derivative first of the power function x to the 5th, which gives me 5x to the 4th, and then I can remultiply in the constant. The proof of this is very similar to the proofs we've already done, so I leave it to you to discover on your own. Let's now take a look at the next two examples, 4 and 5. Pause the video, write out the derivatives using derivative rules, then restart the video and we'll compare. So how did you do? Yes, isn't it easy? It's wonderful. No more taking the limit of the difference quotient. Much simpler to get these results and a lot less work. Let's now take a look at examples 6 and 7. In 7, we want to find the slope of the tangent line. And we want to find the equation of the tangent line itself in order to graph both the function and the tangent line on the graph. Now, in order to do that, we need to find the derivative at that point to know what the slope of the tangent line is. We'll also need what that point's value is on the function to know what point to use in the tangent line. We've done these before, but now we have a fast way of finding the slope of the tangent line. Pause the video, work these both out, then turn the video back on. The result for example 6 is pretty straightforward. Don't forget the derivative of the constant 1 is 0, so you do not need to write it. Now let's look at example 7, where we were to find the tangent line and graph them both. I need to have a point that connects the function and the tangent line. That would be the function value at that point, which is x equal 2. I substitute 2 into the function and I get 1, which is the ordered pair 2, 1. Then I find the derivative using the new derivative rules. The derivative of 3x squared minus 11 is 6x. Notice the derivative of negative 11 is 0. Then I substitute 2 into my derivative function to find the derivative specifically at x equal 2. This gives me the value of 12. I know the point 2, 1 is on my line, so I use 1 for the y, 2 for the x, and 12 for the slope. My hand-drawn attempt was not the greatest, but it does at least get the point across. It looks a lot better on Desmos, where I played with the values of the range on the x-axis to widen the graph so that you could see this slope here. Now, again, we need to verify that these are connecting when x equals 2 and giving us the value of 1. And in fact, that is the case. We now want to talk about the product rule for differentiation. This is not simple. Derivative of a product is not the product of derivatives. A limit, it is. The limit of a product is the product of the limits, and the same for the quotient, not for derivatives. All you can do with derivatives is take out the constant and split apart the addition and subtraction. Those are simple rules, but the product rule and quotient rule are not. Let's now take a look at the actual product rule down here. When I look at the product rule that I see here, you'll notice that I have two differentiable functions, f and g, being multiplied together, and I want the derivative of the product. It gives me the derivative of the first function times regular old second function plus the derivative of the second function times the regular old first function. In other words, the derivative of f times g is f prime g plus g prime f. You need to memorize this because it's going to come up thousands of times in your calculus experience. Let's take a look at the proof of this rather difficult concept. Again, we're going to allow our function j of x to be the product of f and g, and we're going to write the definition of the derivative using the limit of the difference quotient. Then we substitute what J means by rewriting it as f of x plus h times g of x plus h minus f times g. Now we're going to have to apply a bit of a technique here in order to convert these into the derivatives of each individual function and the function itself. The trick is to add and subtract the specific value f of x plus g, or f of x times g of x plus h. Now keep in mind that this didn't happen overnight. It took someone forever to figure this out. They played with it and played with it and played with it and finally found it. We're going to add and subtract this term in the center. This term here is the same. And since we're subtracting it and adding it, we're actually adding nothing to the definition of the derivative. Now we regroup. We're going to group these first two sets together, and we're going to factor out the common g of x plus h. And we're going to group the second two sets together and factor out the common f of x. Let's go ahead and show that work now. We split the quotient into two terms and use the sum law for limits to do this. Now we have the limit of f of x plus h times g of x plus h minus this term we added and subtracted, f of x, g of x plus h, plus the limit that follows it, f of x, g of x plus h minus f times g. Both are divided by h, since these are coming from the definition of the derivative. Now we factor out the common g of x plus h in this first limit and the common f of x in the second limit, as you see in the color-coded section above. When we factor out the g of x plus h and the f of x, you can see that we're starting to realize that this represents the difference quotient for f, and this represents the difference quotient for g. Taking the limit of the difference quotient will give us the derivative. We do still have a product, but we can use the product law for limits to split the limit of a product into the product of the limits. You're allowed to do this with limits. You are not allowed to do this with derivatives. Don't even think about it with integrals. Now we have the derivative of f times the limit of g of x plus h as h goes to 0. But that will just be g of x. And we have the derivative of g times the limit of f of x as h goes to 0, which is just f of x. In other words, we've proved the derivative rule for products is f prime g plus g prime f. It needs to just roll off your tongue. Now we're going to see that there is a quotient rule that is at least as complicated, in fact, more complicated. Before we get there, though, let's practice what we've learned. Go ahead and find the derivatives of these two examples using the product rule. Then turn the video back on and we'll discuss them. Let's now look at these two examples. In the first example, number 8, I have that f is the function 2x to the 5th and g is the function 4x squared plus x. Then I can apply the rule for the product of f and g. The derivative is f prime g plus g prime f. F prime applies the power rule and constant multiple rule. I get 10x to the fourth for the derivative of f. I leave g alone and write 4x squared plus x. Then for the second term, I take the derivative of g, which is 8x plus 1, in parentheses, and multiply by the original function f. Then I can multiply it out and combine like terms to get the result in yellow. Is there an easier way? What would have happened if I multiplied it out first? Would I get the same derivative? I hope so, because it should come out the same. If I multiply out my function, I would get 8x to the 7th plus 2x to the 6th. This would give me a derivative of j of 56x to the 6th plus 12x to the 5th. The same result I got on the left. Why then, do you ask, do we need a product rule? Well, this will only work with functions that are the same type and not all functions. It works with polynomials and it can work sometimes with exponentials, but it's not going to work with a logarithm times a logarithm. And it certainly won't work with an exponential times a polynomial. You're going to need the product rule. Now let's look at the next example. Again, using the product rule, f of x is x plus 2, and g of x is 2x squared minus 3. The derivative of f is 1, and the derivative of g is 4x. I applied the rule for the derivative of the product, and I get f prime g plus g prime f. When I put these in their appropriate positions and multiply it out, combine like terms, I get 6x squared plus 8x minus 3. Method 2 would be more efficient here. It's true. If I were to apply method 2, I would first multiply out j of x, and I would come up with, what would I come up with? Let's see, 2x cubed plus 4x squared minus, I lost myself there for a second, 3x minus 6. And when I take the derivative of that, I get 6x squared plus 8x minus 3, the same result I got using the product rule. Let's now cover the quotient rule for differentiation. As I mentioned previously, it's even more difficult than the product rule. You need to find your own rhythm and pattern for saying it out loud, and you need to use that pattern every time you do it so it becomes a groove in your brain. When I first memorized it, I memorized it as the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That works for me, and it just rolls off my tongue. You might find that you want to use a different pattern, whichever one works. That is, in fact, the pattern. So let's take a look at what the derivative of f divided by g is. It's the derivative of the numerator times the denominator function minus the derivative of the denominator function times the numerator, all divided by the denominator function squared, multiplied by itself. In terms of symbols, this becomes f prime g minus g prime f over g squared. Make sure not to mix the two. The product rule results in a sum. The quotient rule results in a difference divided by g squared. Notice that the 2 in the power position is a true power. It's not in parentheses, so it's not a derivative. The quotient rule proof is very similar to the product rule, so we're going to omit it here. Let's now take this one and work through this one together. In this particular function, my f of x, the numerator, is 3x plus 1, and the derivative of it is 3. My denominator function is 4x minus 3, and the derivative of it is 4. Now, the derivative of the quotient of f with g becomes the following. F prime g minus g prime f divided by g squared. Let's write it out. The derivative of f is 3 multiplied by the g function 4x minus 3 minus the derivative of g, 4, times the f function 3x plus 1, all divided by the denominator function squared. Now, most of the time when we're working with derivatives, it doesn't do us any good to multiply out the denominator part. On occasion it does, but most of the time you can leave that squared. You do need to clean up the numerator though. If you've left enough space, you could work it directly above and write that this gives me 12x minus 9 minus, and then in parentheses, 12x plus 4, which becomes minus 12x minus 4. The 12x minus 12x cancels. Negative 9 minus 4 is going to give me a negative 13. The final result for the derivative of the quotient is negative 13 divided by 4x minus 3 quantity squared. And I would almost certainly leave it in this form. Let's take a look now at the next 3 examples. We want to use the quotient rule to find the derivative of x squared plus 4 and x squared minus 4. You cannot cancel because these are not identical, and everything has to be buried in parentheses before you're allowed to cancel in a fraction. This would be a straightforward use of the quotient rule. Let's take a look at the next one. It's similar, but now they're not the same type of function. We still are going to apply the quotient rule. 13, we want to find the equation of the tangent line to the graph of this function here, the ratio of 2 functions, at the point negative 1, 1. Well, we'll have to have the derivative of the quotient. Go ahead and try these now, then turn the video back on and we'll review our answers. Let's now review these last 3 examples of the quotient rule for derivatives. My numerator function, x squared plus 4, has derivative 2x. And notice my denominator function, x squared minus 4, also has derivative 2x. These are the same function translated vertically up and down. All functions that are identical except for a vertical translation, not a stretch or compression, just a vertical shift up or down, have the same derivative because the derivative of the constant, which gives the shift up or down, is 0. Putting these into the formula, I come up with the expression that you see here. It's always a good idea to multiply out first and then distribute the negative to avoid making a careless mistake. This leads me to the result, negative 16x divided by x squared minus 4 quantity squared. Notice I didn't write g squared until I got to the last step. I knew I probably wouldn't multiply it out, and it just saves time in writing. Let's now look at the next example, example number 12. Example 12, we have a line divided by a quadratic. Again, the derivative of the numerator function is 1, And the derivative of the denominator function is 2x minus 7. Again, we have the function x plus 9 divided by the quantity x squared minus 7x plus 1. Now, when we're looking at this function, we apply the rule for the derivative of a quotient, f prime g minus g prime f divided by g squared. I don't write out the g squared until I get to the very end. You'll notice that these quadratics are not remotely similar. There's no way there's going to be any cancellation. There's no reason to do any further simplification. Let's now turn our attention to the last example that I wanted you to do. When we're looking at this, we have a function 2x divided by the quantity x minus 1, and we want to find the tangent line at the ordered pair -1, 1. The numerator function 2x has a derivative of 2, and the denominator function x minus 1 has a derivative of 1. Putting this into the quotient rule, f prime g minus g prime f divided by g squared leads to the following expression: 2 times x minus 1 minus 1 times 2x. The 2x's cancel when I simplify, and I end up with this expression for the first derivative of that function, -2 divided by the quantity x minus 1 squared. Again, I didn't write g squared until the final step. I need to evaluate this at the ordered pair -1, 1. That means the x value is -1, so I substitute that into my derivative function to come up with the slope at that point of -1/2. Then I'm able to write the equation of the tangent line using that slope of -1/2 and the ordered pair -1, 1. The double negative gives me an x plus 1 in parentheses. Let's take a look at the graph, since we all know I can't graph particularly well. You can see the graph of the function here in red. It is a rational function, and we do see that behavior there. We also can notice, again, that the ordered pair -1, 1 is on the left half, and the tangent line at that point is given by the equation that we found. Now let's go ahead and turn our attention to the extended power rule. We're finally going to get to use the power rule for everything. We'll start by proving it for negative exponents, but you'll have to take my word for it on rational exponents and real exponents. That's really beyond our capability at this point. Let's look at what we're talking about. I've already proved the power rule if the power is a counting number, 1, 2, 3, 4, 5. What if it's a -1, 2, 3, 4, or 5? Well, then I have a problem because the rule I've proved so far only applies to positive exponents. What if instead what I have is something where I want to take the derivative with respect to x of x to the -5? Well, the -5 is not a counting number, so how am I going to get that accomplished? What we're going to do is prove the rule, but before we prove it, notice that the rule is the same rule. That's right. The derivative of x to the -5 will turn out to be -5 pulled to the front as a constant to multiply by and subtract 1 from the power. -5 minus 1 gives me a -6. So the derivative becomes -5 x to the -6. Let's prove the rule now. Assume k is a negative integer like -5. Then if I multiply that by a negative, it would be a positive. We'll let n represent the opposite of k, in this case 5. By the definition of a negative exponent, I can rewrite this as 1 over x to the k. This means that if I have x to the negative 5, I could have rewritten this as 1 over x to the positive 5. And then I could apply the quotient rule. If we apply the quotient rule, notice that it changes the sign from negative to positive when we move it. Now I can apply the quotient rule and the power rule since my power is now positive. Applying the quotient rule, remember that the numerator is a 1. The derivative of a constant like 1 is 0. So for my f prime, I get the derivative of 1 is 0 times the denominator, x to the n, or x to the 5th, minus n, x to the n minus 1, the derivative of the denominator, in my case, 5x to the 4th, times the original numerator, which is 1, all divided by the denominator squared. Rewriting and simplifying tells me that I have negative n x to the n minus 1 over x to the 2n. Since I have two terms with a base of x and they're being divided, I subtract the powers. N minus 1 minus 2n, all multiplied by negative n. Then when I combine n minus 1 minus 2n, I get minus n minus 1, the rule. Back substituting finally to get out of n and back to k, I get the final rule of the derivative of x to the k, even if k is a negative integer, of kx to the k minus 1. In fact, this rule does work for rational values and even for irrational values. It works for all real exponents, but again, it's way beyond our ability to prove. You'll just have to take my word for it. We want to turn our attention now to mixed practice. That is, we're going to be having different rules to apply in the same problem. When we have multiple rules to apply, a good rule of thumb is to apply the rules in the reverse order of how you would apply the order of operation. So if the last thing you do is raise to a power, that should be the first thing you undo with the derivative. Let's take a look at example number 14. In 14, we want to find the values of x for which the graph of 4x squared minus 3x plus 2 has a tangent line that is parallel to the line y equal 2x plus 3. Well, that tells me immediately that the slope of the tangent line has to be the same as the slope of the parallel line. In other words, 2. In that case, I know that f prime of x has to equal 2 since parallel lines have the same slope. Now I take the derivative of my function x, which gives me 8x minus 3, and I set that equal to the 2 and solve for x. This gives me that x is equal to 5/8. To find the equation of the tangent line, I need to know what the ordered pair is where the two graphs connect. So I substitute the value of 5/8 into the original function, 4x squared minus 3x plus 2. If you go ahead and multiply this out, you should come up with the value of 27 divided by 16. Then I know that the tangent line is going to be given by y minus this 27 divided by 16 equal to the slope of my tangent line 2 times quantity x minus 5/8. Let's go ahead and look at the graph of this one. You can see the parallel line here in purple, and notice that the slope is identical to the slope of the tangent line. And the tangent line is here at that value that I gave earlier. Let's now look at example 15. In example 15, we want to find the derivative using the quotient rule first. Then we want to rework the problem by first simplifying the function, since it has a single term denominator, by dividing each term in the numerator by the denominator, then refinding the derivative. We should get the same result. Go ahead and try that now. Let's see what we got. When we apply the derivative rule to this function, we have a bit of an issue because we named this function f and not h. However, as long as you can keep straight in your mind which f you're talking about, and they're not the same, it's okay with me if you rewrite the derivative using the quotient rule as f prime g minus g prime f divided by g squared, where this f is the numerator function for x cubed minus 2x plus 1. It has a derivative of 12x squared minus 2. And the denominator function x squared, which we wrote as g, has a derivative of 2x. When we substitute this into the formula and simplify things, we end up with an expression over x to the fourth power. You'll see here that the denominator x squared gets squared, which gives us x to the fourth. Because it's a single term polynomial, we can divide each term in the numerator by the common denominator. Then this reduces each individual term until we get this expression here. Could I have simplified f first and then done the derivative? The answer is yes, and it would have been easier. The rule is, if you can simplify the function first, do so before you take the derivative. This time I rewrote the function, the original f, as 4x cubed minus 2x plus 1, all divided by x squared. I split it into 3 fractions, each term in the numerator divided by the denominator. Then I simplified each one. Notice that I next used the rule about negative exponents to rewrite -2 divided by x as -2 times x to the -1. And I rewrote 1 over x squared as 1 times x to the -2. Then I applied the power rule and the sum rule and difference rule to take the derivative. This gave me 4 plus 2x to the -2 minus 2x to the -3, which, if I then move the parts with negative exponents, gives me the same answer I had previously. Now, the next problem is rather more complicated. In fact, it's quite a bit complicated. So let's do this one together. Problem 16 says, find the point on the graph of x cubed, which looks like this, such that the tangent line at that point has an x-intercept of 6. Well, now this is kind of a complicated thought. So let's draw a picture and try to visualize what's happening. First, we have the graph of x cubed, which comes up, flattens, goes to a saddle point at the origin, and then continues up. We need to find some ordered pair AB on the graph of x cubed where the tangent line intersects the x-axis at 6. Well, the tangent line, as we know, is straight, so what are our possibilities? well, maybe, I don't know, maybe it's over here, and that intersects here at the ordered pair 6, 0. Maybe that's not it, and actually it's coming down from here. Now, it's hard because of the way I've drawn it to know which of these applies or if they both apply. I can't tell. So I'm going to have to solve the equation without even knowing which side I'm looking at. Now, what does it mean for the point to be on the tangent line and on the graph of f? In this case, being on the graph of f, let's let our point on the tangent line here, or maybe here, we don't know, be AB. To be on the graph x cubed means that f of a equals a cubed, which of course is b. So the value of b is in fact a cubed. Now, we also know that we want to find the tangent line, which means we need the derivative. So the first thing I'm going to go ahead and do is compute the derivative. To compute the derivative, I apply the power rule to x cubed, getting 3x squared. Now I'm looking for the derivative at the ordered pair a comma b. That means that I can substitute a into the derivative to find the slope of the tangent line there. This becomes 3a squared. This is the slope of the tangent line at x equal a. Now, I also know that the slope of the tangent line will be given by the slope between 2 points on the tangent line. And I have 2 points on the tangent line. My ordered pair AB and the x-intercept 6, 0. So let's compute the slope of the tangent line using the slope of the line. This is going to be with my 2 ordered pairs, AB and 6, 0, B minus 0, y2 minus y1, over 6 minus A, x2 minus x1. This, however, reduces, and oops, I've got it backwards. Oops, bad. Instead, I have the A under the B minus 6. And this gives me another formula for the slope of the derivative at the point AB, which is B divided by A minus 6. Now, I know these have to be equal to each other, so let's set them equal and solve for A or B. Now, I've got both A and B in my equation now, that 3a squared equals b divided by a minus 6. I need another equation to solve the system. I have it, though, because ab's on the original function, x cubed, which tells me that b is a cubed. I can replace the b with a cubed. Now, to solve this equation, the simplest thing to do is to multiply both sides by the denominator factor, a minus 6. This is going to result in the following equation. 3a squared times quantity a minus 6 becomes 3a cubed minus 18a squared. And on the right side, the a minus 6 is canceled to get a cubed. Move everything to one side and solve for a. This gives me 2a cubed minus 18a squared equals 0. Or, factoring out the common factor 2a squared, I end up with 2a squared times the quantity a minus 9 equals 0. This means that either a equals 0 or a equals 9. If a is 0, where am I on the graph of x cubed? I'm at the saddle point. But that can't be right because I know at that point, the derivative goes horizontal. It's got to have a slope of 0. So that's not the right point. Instead, it's also an x-intercept. Instead, what I have must be 9. It must be the case over here on the right, and chances are it's much further out. Let's move our blue dot up where it belongs, probably somewhere up here, further out, and we've got our slope coming down here. This is on the graph out there at 9. Now, this graph is not remotely to scale, because if A equals 9, then what's B? Yes, it's 9 cubed. That means that my ordered pair for that point is 9 cubed, or 729. I can also now find the slope of the tangent line by substituting 9 into the derivative formula. And that will give me 81 times 3, which is 243. 3 times 9 squared, which is 243. The equation of my tangent line is y minus 729 equals the slope 243 times x minus 9. Notice this is a super steep line. We will think it's vertical because it will look vertical. Now I've gone ahead and graphed this for you, and I've played with the lengths of the units on the x and y axis so you can see everything at the same time. That makes that line not look nearly vertical, when in fact on a regular graph it would, which I'll show you in a second. You can see here I'm only graphing between -8 and 12, but I'm graphing between about -400 and 1,000 in order to get it all on the graph at once. And you can see up there that that is where those two connect. Now, if I were to graph this where the unit on the horizontal and vertical are the same by clicking here, you can tell that the tangent line looks vertical. It's right out here coming through 6. We can't tell it's anything but vertical, but in fact, it has a positive slope. Let's now turn our attention to problem number 17. 17 wants us to find the equation of the line that passes through the point 3, but is tangent to this graph. Well, if it's tangent to the graph, it must be touching the graph. So we better make sure that 3 does satisfy this equation. When I substitute 3 for x, I get 2, and 6 divided by 2 is 3. So it is a place where they connect. To get the equation of the tangent line, I need to find the derivative. I can rewrite f of x as 6 divided by x minus 1. Then I can let my other f be equal to, and these are quote marks. Maybe I make them look more like quote marks, 6, where the derivative of that is equal to 0. And my g becomes x minus 1, and the derivative becomes 1. Now, when I apply the quotient rule to the original function f, I get my fake f prime times g minus g prime times fake f, all divided by g squared. This is going to give me 0 times x minus 1 minus 1 times 6, all divided by g squared. This comes out to be 0 for the first term, -6 divided by the quantity x minus 1 squared. This is the derivative function anywhere on the domain of that graph where the derivative is defined. Now we want to find the derivative at x equal 3. So the derivative at x equal 3 is found by substituting 3 for x, and we get negative 6 over 3 minus 1 squared, which gives us negative 6 over 2 squared, or 4, or negative 3 halves. Once we have negative 3 halves, we already have our point, and we can simply write y minus 3 equal negative 3 halves times x minus 3. Let's look at the very last problem in this section. Example 18 is an application problem talking about the number of Arctic flounder in the Atlantic Ocean. It's modeled by this rational function given by the quantity 8t plus 3 divided by the quantity 0.2 t squared plus 1. In this case, this is representing the population in millions. So if I get a 2, it means 2 million. The t is measured in years. The first part of this question wants us to find what the initial population of the flounder in the Atlantic Ocean is at the point in time where we start using this model. In essence, part A is asking us to find P of 0, which becomes, when we simplify our formula, simply 3. This means we actually have 3 million Arctic flounder in the Atlantic Ocean at that point in time. Now, the second part asks us to define the derivative of the population after 10 years, when t equals 10. To do that, I'm going to let f of x be 8t plus 3 and take the derivative with respect to t. Then f prime, and I should write t, f prime of t is equal to 8. The denominator is going to represent g of t, which is 0.2 t squared plus 1. G prime of t is equal to 2 times 0.2, or 0.4, times t. Remember, the derivative of a constant is 0. Now I can put this into my quotient rule. The derivative of population with respect to time, written dp dt, is equal to f prime g minus g prime f divided by g squared. F prime is 8, g is given by 0.2 t squared plus 1, g prime is 0.4 t, and f is 8t plus 3. All of this is divided by g squared. Go ahead and pause the video and work out the formula and then evaluate it when t equals 10. Come back and we'll interpret that result. Now that you've worked it out, I hope that you ended up with this simplified expression over here on the right. Negative 1.6 t squared minus 1.2 t plus 8, all divided by g squared. When I substitute 10 in place of time, I end up with the proper fraction negative 164 divided by 441. This turns out to be about a negative 0.3719. It represents in millions the number of flounder that we are losing each year. In other words, we have a decrease at 10 years of almost 300, well, more than 370,000 flounder a year. Given that we only started with 3 million, this would be very concerning. Now, for our next video, we're going to be taking a look at the derivative differently. In our next video, we're going to be taking a look at the derivative as a rate of change. The derivative is a rate of change. It's the slope of a tangent line, but it's also a representation of how one variable changes with respect to another. So you can expect more application problems in the next section. I hope you'll join me there.